So this is my lab for magnetic braking with Faraday. So table of contents wise, I'll be going through the introduction, key ideas and fundamentals, purpose, results preview, the experiment itself, assumptions, experiment part 1, coding part 2, and then finally coding part 3. I'll be going through the possible errors and then finally the what if questions. So in terms of key physics fundamentals, I'll be going through Faraday's law, which is to induce EMF equals the number of loops times the rate of change of flux with time. Ohm's law, which is the electric current equals the voltage divided by resistance. Next is Newton's second law. Acceleration of an object is directly proportional to net force and inversely proportional to mass. And then Newton's third law for a reaction, there is an equal and opposite reaction. The purpose of this lab is to collect observational data of a magnet flying through a conductive tube of an aluminum foil. In addition, model the tube/magnet interaction and compare predictions with observed data. So in terms of results preview, the experiment time was found to be 0.82 seconds on average, while the computed time was 0.744 seconds, which is a noticeable difference. So experiment assumptions, the forces from the loop itself and the gravity are the only forces acting in the loop, and the magnet will fall down with the North Pole also facing down. So experiment part 1, first we mark the North Pole of the magnet. Hold the magnet above the foil, which should be vertical, and then drop it in. Record how long it takes for the magnet to fall. Repeat the steps 4 more times, and then take the average. Next, the foil width was 0.005 meters. The inner foil radius was 0.0183 meters. The tube length was 0.048 meters, and the magnet mass was 0.02 kilograms. And the magnetic dipole was 5.6. Run 1 was 0.85, run 2 was 0.81, run 3 was 0.88, run 4 was 0.79, run 5 was 0.8, and the average run was 0.82 seconds. So in terms of coding, the first thing I did was initialize the length of the tube with the foil in a radius of 2, and then the radius itself. Next, I created tube of aluminum foil as a series of rings stacked along the y-axis, and the y-axis is perpendicular to the plane of each ring. Next, I created the bar magnet, so this is where I added the properties, which is the mass and then the magnitude of magnetic dipole moment. And then I also visualized the bar magnet itself, and then I left the initial conditions the same. Next, I created a function to calculate the magnetic field of the bar magnet, and you can see dipole B is the function that does it. And I also and then next I created a function to calculate magnetic flux, and I calculated the flux through each ring due to the falling magnet, which you can see there. Then I also created a simulation loop, which you can see there. And then finally, step 7, I calculated the gravitational force on the magnet, calculated the magnetic force on the tube on the magnet, computed the flux for a ring due to the falling magnet, and then calculated the current in the ring, and then I visualized each one. Next, I also computed the typical B field at each ring. You can see that on the 4 lines, calculate the magnetic force on the magnet, and then updated the magnet's velocity and position, and then I also outputted the time it took for the magnet to fall. Results-wise, you can kind of see as the time increases, the velocity rapidly decreases and remains stable after around 0.2, and so you can kind of see that the time in 2 was 0.744 seconds, and this might have been possible to incorrect timing due to human error, math computational error, and then measurement error of foil dimensions and magnet weight. So what if the resistivity of the conductors were reduced as close to possible to 0? How would the dynamics of the falling magnet change? If the resistivity of the conductors were reduced as close as possible to 0, then it causes there to be larger induced currents. This will then cause the magnetic field to be stronger, and this increase in magnetic force will then cause the magnet itself to have a stronger opposing force and fall slower. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? If holes or slots were cut into the tube, then this would lead to decreased induced current and cause the induced magnetic field strength to decrease. The ring current would be disrupted, and this would then cause the redistribution of the holes themselves and the magnet falling faster. Thank you for listening to my presentation.